Okay, this video is about the implicit function theorem. And in calculus, you're probably familiar with implicit differentiation. So in implicit differentiation, you might have something like x squared plus xy plus y squared equals 6. And you want to find what dy dx is at a certain point on this curve. And here you're given a relationship between x and y. And the point is that, okay, this is going to be some curve, and at some particular point on the curve, the graph looks like the graph of a function. And so you can use something called implicit differentiation to find y prime. And this implicit function theorem is a theorem that tells you when you can implicitly have a function y which is in terms of x. And it's a general theorem, but I'm only going to state a special case. So a reference for the general implicit function theorem is the book by Munkres, Analysis on Manifolds. Okay, here's a special case of the theorem. So let A be an open set in R2, and let f be a function, a real valued function from A of class C infinity. Actually, we don't need C infinity, we just need, I'm pretty sure we just need class CR, but I'm assuming, okay, so it's not strictly necessary to have C infinity. It's just for simplicity. I mean, I think it's true for functions with a continuous derivative, so C1 functions. And suppose that you have a point a comma b in A, and that f of a comma b is 0, and that the partial derivative of f with respect to y evaluated at a comma b is not 0. Okay, so suppose that you have this, then there is a neighborhood b of a in R, and a unique continuous function g from B into R such that g of A equals B and f of x comma g of x is 0 for all x in B. And moreover, the function g is C of class C infinity. Okay, so we won't prove this theorem, but we'll just illustrate this theorem. This is the implicit function theorem. And there's a general statement for functions from Rn into Rm. But anyway, let's just look at an example. So let's say that you have a function from R2 to R, which is defined by f of xy equals x squared plus y squared minus 5. Okay, so this function, so here we can just take A to be all of R2. And suppose that you take the point A comma B, which is 1, 2. So this is a point in R2 such that f of AB is 0, right? Now, what's partial f partial y? So partial f partial y is 2y, and so partial f partial y evaluated at AB is definitely not 0. So the conditions of the theorem hold, and the theorem says that there's a neighborhood B of A in R2. Okay, so A is 1. So what's going on is, so here's A equals 1. There's a neighborhood B of A in R2, and the unique continuous function G from B into R, so this open interval is B, G into R is such that G of A is equal to B, so G of 1 is equal to 2, and such that f of x comma g of x is 0. Well, let's look at the graph of f of x comma y equals 0. So the graph of f of x comma y equals 0 is x squared plus y squared equals 5. So it's a circle of radius square root of 5 centered at the origin. Okay, that doesn't look centered at the origin, but it's supposed to be centered at the origin. And it has radius square root of 5. Okay, and there's supposed to be a function g such that f of x comma g of x equals 0. In other words, g of x for all x and b is on the blue curve. So you might have something like this. Right? This would be y equals g of x. So locally you can solve for y in terms of x. And in this case you can actually see what y is going to be. Y is equal to the square root of 5 minus x squared on this open interval b. Right? Okay, now let's take a different example and let's look at a comma b equals the square root of 5 comma 0. Now this point is also on the circle, but partial f partial y evaluated at this point is equal to 0 because partial f partial y is just 2y. So the theorem doesn't tell you anything, and in fact what happens is at root 5 comma 0, right here, there is no interval neighborhood b of root 5 and a continuous function g satisfying the properties of the theorem. Okay, let's see what else can happen. So let's say that you have f of x comma y equals x squared minus y cubed. And the graph of this function looks like that. And partial f partial y is equal to negative 3y squared. So at 0, 0, right, the implicit function theorem doesn't tell you anything. And what happens is that we can solve for y in terms of x near 0, 0. Right? You do have a continuous function near 0, 0, but this function is not differentiable at 0, 0. But the theorem, the implicit function theorem, tells us that anywhere else, locally, you can solve and get a differentiable function. Let's take a look at one more example. So let's say that you have the function from R2 to R, which is defined by f of x, y equals y squared minus x to the fourth. Well, so let's take a look at the graph. So here's the graph of x y equals 0. And let's look at the graph of f of x, y equals 0. That looks like, well, if f of x, y equals 0, that's if and only if y squared equals x to the fourth. And so you get y equals x squared and y equals negative x squared. So it's like this and then like that. That's the graph of f of x, y equals 0. And partial, this goes through the origin, of course. So partial f partial y is equal to 2y, and this is 0 if and only if y is equal to 0. Now let's see what happens at 0, 0. So we can solve for y in terms of x near 0, 0. But what happens is the resulting function is not unique. Right? Because you have this piece and you also have this piece that you can solve for near 0, 0. And in the statement of the implicit function theorem, there's a unique continuous function g, such that these two properties hold, that g of a equals b and f of x comma g of x is 0. But anywhere else, right? Anywhere else, there's a unique way to define g. It's just y equals x squared or y equals negative x squared, depending on which point you're at. Okay, so that gives you some examples of where the implicit function theorem doesn't hold. And yeah. Okay, thanks for watching.